The way that species affect nutrient cycling, both for nutrient inputs and nutrient turnover rates, it's complicated and there's a lot of interactions that occur. But we do know that species impact nitrogen cycling or nutrient cycling in a couple of different ways. Just like species can certainly impact nutrient cycling, they can also impact biophysical processes. Species effects on microclimate influence ecosystem processes more strongly in extreme environments. So this statement is that you have to go to environments where climate has an overriding impact on the functioning of the ecosystem. And when you go there, the species effects on microclimate are going to become more important. So when you want to really take a look at a place where species strongly impact ecosystem processes by affecting microclimate, you're going to want to go to the hottest places or the coldest places, the driest places or the wettest places, not necessarily the most mesic ones. One example is essentially the ability of species to differentially insulate. And what that means is that we know that ground heat flux is important and the ability of ecosystems to absorb energy in the soils and those soils to heat up. In cold ecosystems, that ground heat flux is important for thawing soils out. But what happens if you have a species that sits on top and is able to insulate against ground heat flux, but have it differentially insulate such that it's more likely to let heat escape than it is warmth to get into the soils? If this happens, the soils are going to get colder and colder and colder over time, and the amount of thawing is going to be a lot less. That's a situation that happens with ecosystems that become dominated by sphagnum moss. Sphagnum moss is a differential insulator. It insulates a lot better during the growing season than it does during the winter. So it allows heat to escape relatively well during the winter, but it has good insulative processes that block heat gain during the summer. When sphagnum moss gets into these cold systems, a couple of changes happen, but one of them is that the soils on average get a lot colder. In addition, species have the ability to impact canopy roughness. So some species form a much smoother canopy, for example, such that when wind goes across it, it's not going to have as much convective loss of energy, as opposed to other species that might form a rougher canopy and cause a lot more convection to occur. In addition, other species are going to differ in their albedo or latent heat flux. So by differing in your albedo, there's going to be differences in how much energy is absorbed versus reflected. And if you absorb a lot more of that energy, it's going to heat up the ecosystem. And latent heat flux for the same reason. How much energy goes into transpiring water or evaporating water, as opposed to being absorbed and causing sensible heat flux. So we know that species are going to differ, and some of these differences are going to be in albedo and latent heat flux. One of the examples that the authors give are really in post-fire forests. And in a lot of northern ecosystems, the species that come back really determine some of the trajectories and differences in ecosystem processes. So if it's a deciduous species versus an evergreen species, we get big impacts on how that ecosystem functions. So this is an example of a burn in the boreal forest, and you can see that these burns can often be really dark and they can absorb a lot of heat, but sometimes the species that replace the spruce that was there are going to be deciduous species, and they function a lot differently than having spruce come back. The canopies are a lot less rough, but you can see there's probably a lot more albedo and they evaporate more water. On the other hand, the post-burn systems have a lot of sensible heat flux because they absorb a lot of that radiation, and often these spruce systems too don't transpire as much water, but instead you get a lot more sensible heat flux. So the ecosystem is a lot cooler if it's dominated by deciduous species than these coniferous species too. Here's some data to help show that. If we take a look at differences in albedo between conifer and deciduous species, albedo is a lot higher for deciduous species, sensible heat flux is a lot lower, and evaporation rates. All of that means is that in the conifer, when you put that all together, these conifer systems are going to be a lot hotter, and these are going to end up being a lot cooler. So we'll get big differences in the temperature of the ecosystem based on their characteristics in terms of albedo, sensible heat, and evapotranspiration.